My name's Jack, and I'm a PhD student here at the University of Birmingham. In geology, the term salt can encompass any rock which form mainly through evaporation. This is Rory, by the way. When oceans dry up and evaporate, they leave behind minerals that precipitate out. The first of those is calcite, which you can find in caves, stalactites and stalagmites. The next of them is gypsum, which you can find on your walls at home. And then the mineral after that is halite, or table salt, which you'll put on your fish and chips on a Friday. And this is what I study for my PhD. I study salt. Let me explain something. Salt is unique. It's made out of crystals, but it's weak.
Once a layer of salt has formed, it will be covered in sediment. In this case, mud. Salt is incompressible, which means as it gets buried, its buoyancy will remain the same, whilst the rocks around it will become denser. I'm studying the ways in which the salt deforms and interacts with the sediments adjacent to it using magnetics. As it is buried, the base of the salt sinks, but the top of the salt remains at the surface, eventually resulting in the underground salt structures that can be kilometres deep. These are called diapirs, and the process of salt movement is called halokinesis. Salt is also impermeable to fluids and gases, meaning that it's economically important when it comes to oil and gas. But salt doesn't occur just anywhere around the world, so I went to Nova Scotia to study the Carboniferous Age rocks there. In Nova Scotia, I could retrieve halite samples for magnetic analysis from a working salt mine. The gypsum at the surface is at the top of a 3-kilometre deep salt diapir and shows signs of extreme deformation that can be related back to geological events of the past. To study the way the salt has deformed, I had to collect orientated samples so that our laboratory measurements could be relocated to nature. By using drones, we can create 3D models of the structures seen in the gypsum exposures, and this helps us correlate them across cliff sections.
Now you know how and why I collected the rocks, it's time to get dirty in the lab.
I start by drilling the rock samples into cores. This capper punch rotates the samples in very low magnetic fields, showing us if there is any alignment of magnetism in the rocks. This might be due to impurities in the rock or because of the mineral crystals. Through 3D modelling, I can then compare the magnetic fabrics with the visible gypsum structures. And to find out what is producing the magnetism, I use extremely high magnification images of the sample surfaces. This PhD is a novel use of an established technique called Anisotropy of Magnetic Susceptibility.